Hey everyone, I'm Dar.
I'm Gun.
I'm Jackson.
I'm Evan.
I'm Nick, and we're doing Chapter 5 Integration.
Use substitution is a method for finding integrals by substituting complex terms for a simpler variable. So in this example, we have the integral of 2x plus 5 times the quantity x squared plus 5x to the 7th dx. And so we're going to let u is equal to x squared plus 5x, and so du is going to be equal to 2x plus 5. And whatever we set u as, du must be in the original integral. So here we have u, here we have du, which is the derivative of x squared plus 5x. The integral of 2x plus 5 times the quantity x squared plus 5x to the 7th dx is going to be equal to the integral of du times u to the 7th. And so taking the integral of du times u to the 7th gives us u to the 8th over 8 plus c, and plugging u back into this equation here, we get 1 over 8 times the quantity x squared plus 5x to the 8 plus c.
Okay, so now we're going to go over integration by parts. Let's say you have an integral with two different functions, the integral of f of x g of x dx. We would then use the equation uv minus the integral of v du as the integral where u equals f of x and dv equals g of x, and you would derive and integrate respectively. You can also remember the equation uv minus the integral of v du using the acronym ultraviolet super voodoo. For example, if we were to find the integral of x ln x dx, we would let u equal to ln x and dv equal to x dx. We would then derive ln x to equal 1 over x dx and integrate x dx to x squared over 2. Following uv minus the integral of v du, we would come to x squared ln x minus the integral of 1/2 x dx, and that would come out to x squared over 2 ln x minus x squared over 4 plus c. Integration by parts is also applicable to any two different functions f of x, g of x. For example, if we were to find the integral of e to the x cosine x dx, we could let u equal to e to the x and dv equals cosine x dx, derive and integrate respectively, and we would come out to e to the x sine x minus the integral of e to the x sine x dx. From there, we would use integration by parts again, and let u equal to sine x and dv equal to sine x, where we would derive and integrate, and come to e to the x sine x minus the bracketed negative e to the x cosine x plus the integral of e to the x cosine x dx. Here, we notice that the integral that we are solving for, e to the x cosine x dx, is equal to the value e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. We notice that at the end, the integrals are the same, so we can add the integral of e to the x cosine x dx to the other side, where we get 2 to the integral e to the x cosine x dx equals e to the x sine x plus e to the x cosine x, and we would then divide by 2 to get our answer. When using integration by parts, there's an order for what you should choose as your u. First, look to see if the problem has inverse functions like ln x, arcsine x, etc. Then look to see whether the problem has polynomials, then exponential and trig functions, and finally constants.
The next method we'll be using is trig substitution. Trig substitution utilizes a simpler variable for a more complex integral. The example will be integral of the square root of 25x squared minus 4 over x dx. Here we'll draw a right triangle to look for the variables. So here I've put theta as the angle, and the hypotenuse will be 5x. So sine theta will be equal to the square root of 25x squared minus 4 over 5x, and secant theta is equal to 5 over 2x. That gives you the respective dx. You plug that back into the original equation, and you get 2 over 5 integral 5 sine theta secant theta tan theta d theta is equal to 2 integral tangent squared theta d theta. That simplifies to 2 times the integral of secant squared theta minus 1 d theta, which is equal to 2 times quantity tangent theta minus theta plus c. We're plugging back in for theta. You get tan theta is equal to square root of 25x squared minus 4 over 2. And theta is equal to cosine inverse of 2 over 5x, which gives you the square root of 25x squared minus 4 minus 2 cosine inverse the quantity 2 over 5x plus c.
Okay, calculus is nothing without application to nature. So here we have the graphical proof of kinematics, where we look at two different lines, one horizontal line and one with the slope of, say, x. If we look at the graph with the slope where there is no slope, and the position x of t and velocity v of t are the same, that means that because the position and velocity are constant at all times, there is no change in position, therefore no change in velocity, and therefore there is no change in acceleration as well. If we look at the other graph where the slope is x, where position x of t and velocity v of t are also the same, and we look that the slope is equal to the change in x over the change in t, which is therefore velocity, therefore dx over dt, that means that we can establish that there's change in position, which means that there is also a constant velocity since it is going at the same pace over time. Any change in velocity means that the acceleration is constant as well. So the slope is equal to the change in velocity over change in time, which is equal to acceleration, therefore dv over dt.
Okay, the next concept we're going to go over are integrals in the form of two different ways. The first one is being the integrals of cosine and sine to different degrees. And so in these forms, there's three different cases you have to take care of. The first is when you have cosine and sine. If your degree for your cosine is odd, then you want to subtract 1 and take that factored out cosine and put it next to the dx. And then from that, you're going to be able to let u equal sine x and du equal cosine x dx. The second case, if n is odd, then you're going to factor out a sine x. So then you'll have u equal cosine x and du equal sine x dx. And the last case, if m and n are both even, then you can just use identities to simplify the integral and solve it from there. So some examples are, let's say you have the integral of cosine cubed x sine x dx. You can tell that the cosine x has a odd degree, so you can factor out a cosine x, and so you can make it the integral of 1 minus sine squared x due to the trig identities, sine x cosine x dx. And then from there, you can distribute to the 1 minus sine squared x to make it the integral of sine x cosine x dx minus the integral of sine cubed x cosine x dx. Then remember to let u equal sine x and du equal cosine x dx, so you can simplify it to the integral of u du minus the integral of u cubed du. And then taking the integral of that, you have 1/2 u squared minus 1/4 u to the 4th, and then you just plug your u's back in to make it 1/2 sine squared x minus 1/4 sine to the 4th x. So our other example is when you have sine x being to an odd degree, which, like in this example, is the integral of cosine squared x times sine cubed x dx. And so this one, you're going to remember to factor out a sine x. So you're going to have the integral of cosine squared x, sine squared x, sine x dx. And then because of trig identities, you can make that into the integral of cosine squared x times 1 minus cosine squared x times sine x dx. Remember to distribute, so you have the integral of cosine squared x sine x dx minus the integral of cosine to the fourth x sine x dx. And then let u equal cosine x and du equal negative sine x dx. So you get the negative integral of u squared du minus the negative integral of u to the fourth du, which becomes negative 1/3 u cubed plus 1/5 u to the fifth. And then plug your u's back in and you get negative 1/3 cosine cubed x plus 1/5 cosine to the 5x. So the next example to this concept is when you have the integral of an integral that includes tangent and secant. And so again, there's two different cases. They're pretty similar to the sine and cosine ones, just a little different, so make sure you pay attention. The first case is when m is odd, and so that's the exponent above the tangent one. And so in this situation, what you're going to do is factor out a tangent and a secant. And so you're going to have the integral of tangent x times secant x times tangent x secant x dx. And you're going to want to let u equal secant x and du equal secant x tangent x dx. Case 2 is when n is even, so the exponent above the secant. And what you're going to do this time is you're going to factor out two secant x's, and so you're going to have the integral of tangent x secant x times secant squared x dx. And you're going to let u equal tangent x and du equal secant x squared dx. And then case 3 is m is even and n is odd. And this time you can just use your trig identities to simplify it and solve it like a normal integral. So I have a couple examples to show you guys. The first one is an example of the case 1. It's the integral of tan cubed x times secant squared x dx. And since tangent cubed is an odd integral, what you're going to do is factor out a tangent and a secant x. So you're going to have the integral of tangent squared x times secant x times tangent x times secant x dx. And then you can use your trig identities to take out the tangent squared x and make it into secant squared x minus 1. And so you're going to have the integral of secant squared x minus 1 times secant x times tangent x times secant x dx. And then you can distribute to make it the integral of secant cubed x tan x secant x dx minus the integral of secant x tangent x secant x dx. And then remember, you're going to let u equal secant x and du equal secant x tangent x dx. And then from there, you're going to plug in your u's. You're going to have the integral of u cubed du minus the integral of u du. And then you're going to take the integrations of that, and you're going to have 1/4 u to the 4 minus 1/2 u squared. And then plugging your u's back in, you're going to have 1/4 secant to the 4x minus 1/2 secant squared x. This next example is actually an example of a both case 1 and case 2 integral. And so that's because you have an odd tangent exponent and an even secant exponent. So in this example, it's the integral of tan cubed x times secant to the fourth x dx. So what you're going to do is you're going to take out both a tangent and a secant, and so you're going to have the integral of tangent squared x times secant cubed x times tangent x secant x dx. You're going to use your trig identities again to make it the integral of secant squared x minus 1 times secant cubed x times tangent x secant x dx. Then you're going to distribute to make it the integral of secant to the fifth x tangent x secant x dx minus the integral of secant cubed x tangent x secant x dx. Remember to let u equal secant x and du equal secant x tangent x dx. And so you're going to plug in your u's and get the integral of u to the fifth du minus the integral of u cubed du, which integrates to 1/6 u to the 6 minus 1/4 u to the 4. Plugging your u's back in, you're going to get 1/6 secant to the 6x minus 1/4 secant to the 4th x.
Okay, so when you have eliminating sine and cosine, you're going to start by using this table over here. So you're going to initially take u, and it's equal to tangent of x over 2, which you'll use later. Dx is equal to 2 du of 1 over 1 plus u squared. Whenever you have sine of x, you're going to swap in 2u over 1 plus u squared. Whenever you have cosine x, you're going to swap in 1 minus u squared over 1 plus u squared. So in this example over here, where you have the integral of dx over 1 plus cosine x, you're going to put in at the top 2 du over 1 plus u squared for dx. 1 stays the same, plus cosine x goes to 1 minus u squared over 1 plus u squared. And then it's just a little bit of algebra to solve down and get an easier integral. And you're going to get this mess here by taking 1 and just doing 1 plus u squared over 1 plus u squared to solve this easier, which comes out to the integral of 2 over 1 plus u squared times 1 plus u squared over 2, because 1 plus u squared plus 1 minus u squared cancels out those, and then you flip the whole thing over and get 2, and then you have your 2 canceling with your 2, and your 1 plus u squared canceling with your 1 plus u squared, which makes a very simple integral of du, which is equal to u plus c, and then from the beginning, where you had u equals tangent of x over 2, you sub that back in, and you get tangent of x over 2 plus c. And then, just to verify that you have the correct integral, you run through and derive tangent of x over 2 plus c. The c goes away, and it leaves you with 1/2 secant squared of x over 2, which is equivalent to 1/2 of 1 over cosine of 2 cosine squared of x over 2, which, with a little bit of algebra, will solve down, and you will ultimately find that you get the same exact integral.
Okay, another technique for integration is by completing the square. Say we want to integrate a quadratic function, ax squared plus bx plus c equal to 0. Integrating the integral of 2x plus 3 over 4x squared plus 12x minus 1 dx is easy enough. You just substitute u for 4x squared plus 12x minus 1, and you come out to 1/4 du 2x plus 3, and you would get 1 over 4 integral 1 over u du, where you would get your answer, which is the 1/4 ln of 4x squared plus 12x minus 1 plus c. But say we have the integral of the square root of x squared plus 4x plus 5 dx. We would then complete the square, and that would come out to x squared plus 4x plus 4 minus 4 plus 5, and you would get x plus 2 squared plus 1. You would substitute this for the integral that we have, and we would come to the integral of the square root of x plus 2 squared plus 1 dx. Here, we then realize that we can use trig substitution and substitute x plus 2 for tangent theta, and make x equal to tangent theta minus 2, and then derive getting dx equals to secant squared theta d theta. Here, we would then use the trig substitution to substitute back into our integral, where we would arrive at secant cubed theta d theta. We would then get ln of the absolute secant theta plus tangent theta plus secant theta tangent theta over 2 plus c. We would then use the right triangle from trig substitution to establish that tangent theta is equal to x plus 2, and secant theta is equal to the square root of x squared plus 4x plus 5, and we would arrive at our answer. We can also use completing the square to solve integrals like the integral of 1 over a to the x squared plus bx plus c dx. For example, say we have the integral of 1 over 2x squared minus 3x plus 2 dx. First, we complete the square, where 2x squared minus 3x plus 2 is equal to the quantity of 2 times x squared minus 3 over 2x plus 1. We would complete the square inside here to arrive at 2x squared minus 3 over 2x plus 9 over 16, subtract 9 over 16, and then add the 1. We would then come to 2 times the bracketed quantity of x minus 3 over 4 squared plus 7 over 16. We would thereby substitute to 1/2 of the integral of dx over x minus 3 over 4 squared plus 7 over 16. We would then let u equal to x minus 3 over 4 and derive getting to du over dx. Du equal to dx. And we would then realize that the integral looks like 1/2 of du over u squared plus 7 over 16, which is the tangent inverse identity. And we would get the answer 1/2 times 4 root 7 over 7 arctangent 4u root 7 over 7 plus c. And then we would substitute u, which is equal to 4x minus 3.
The next method of integration would be eliminating roots. Here's an example. The integral of 1 over x to the 1/2 plus x to the 1/3. Here we allow x to be equal to u to the 6th. So dx is equal to 6u to the 5 du. Substituting that in, we get the integral of 6u to the 5th du over u cubed plus u squared, which simplifies to the integral of 6u cubed over u plus 1 du. This simplifies with the neat trick, 6 integral of the quantity u cubed plus 1 minus 1 over u plus 1 du. Factoring out the 6, you get 6 integral u cubed plus 1 over u plus 1 du minus 6 integral 1 over u plus 1 du, which is equal to 6 integral the quantity u squared minus u plus 1 du minus 6 integral 1 over u plus 1 du. Taking the integral of everything, you get 6 times the quantity u cubed over 3 minus u squared over 2 plus 1 minus ln u plus 1 plus c. Here we establish that u is equal to x to the 1 over 6. So the final answer will be 6 times the quantity x to the 1/2 over 3 minus x to the 1/3 over 2 plus x to the 1/6 minus ln x to the 1/6 plus 1 plus c.
Our last technique for integration is called partial fractions. When you have an integral, such as the integral of 1 over x squared plus 2x dx, you can factor out an x in the denominator and get 1 over x times the quantity of x plus 2. When you have something like this, you can create an equation, such as 1 over x times x plus 2 from the integration is equal to a for any random variable over x plus b, just another random variable, over x plus 2. You then multiply the denominator from the integration to both sides, which will be end up canceling, and you will get 1 equals a times x plus 2 plus b times a to the x. Simplify down and you get 1 equals ax plus 2a plus bx. And then you separate into systems of equations and you get 2a equals 1 because on the other side there's no x, so x is going to equal 0. All things attached to an x are going to equal 0. You can divide the x out and get a plus b equals 0. And 2a is going to equal 1 because there's no x on this side. And then you simplify out and get a equals 1/2. And then you simplify down on this side and get a plus b equals 0, a equals negative b, and b equals negative 1/2. Go back to your main integration, and you get 1/2 the integral from a to the x over here. You're plugging a back in. Dx minus negative 1/2 for b of 1 over x plus 2. Keep solving down, and you get 1/2 the natural log of x minus 1/2 the natural log of x plus 2. Don't forget c. And then your final looks like 1/2 the natural log of x over x plus 2 plus c.